Hey Chem Gang, got a little follow-up video for you today. We've got a little new twist on what we did yesterday, which was trying to separate ions in solution. So yesterday we were just trying to take one ion out of solution, say carbonate. But today we've got two different ions in the solution of the same type, and we want to separate those two. In other words, we want to take out carbonate without taking out chloride, or vice versa, so that the carbonates and chlorides will be separated from each other. Once again, a note about the models. I haven't even shown the waters at all because it would be crazy complicated. And don't forget, you can't have carbonate or chloride in solution without a cation. So originally there would have been a whole bunch of sodiums all around that belonged with the chlorides and the carbonates or something like that. And again, these are going to be spectators, so I'm just going to remove them now. It would have to be some kind of ion that was fairly unreactive, and we're not going to be concerned with the cation spectators in solution. So now we can focus just on the two ions we want to separate. And the idea is we want to create a precipitate with one of these, but not the other. All right. So let's take a shot first with barium nitrate. So that would be, say, 1 barium nitrate formula unit in solution, and I'm going to add some others in. Again, just randomly spread the ions around. So now we've got barium nitrate in solution. And the real key to what I just added is the cation, because I had anions that I was trying to separate, and the question is, what's the cation going to do with them? So as always, you're going to have to check your solubility rules. And what you're going to find is that barium and carbonate is insoluble, so they'll tend to make a precipitate. But barium and chloride is soluble. So wherever barium runs into chloride, again, they'll associate for a bit, but then they'll get bounced off from each other. But when barium runs into carbonate, it starts to make that crystal lattice, okay, and makes that precipitate that starts to fall to the bottom of the solution. All right. So now again, we have a precipitate at the bottom of the solution, which we can filter out. And the chlorides will still be dissolved in the solution, but the solution will just have chloride ions, and we'll take out all of the carbonate ions. Okay? In order to do that, you have to add enough barium to get the carbonate out, but that's easily done. Right? So solid barium carbonate separated from aqueous chloride now. So that's one that works. Okay. What about stuff that doesn't work? So instead of barium nitrate, let's try something different. So now I'm going to go with silver nitrate. All right, so again, here's a 1 formula unit of silver nitrate going in, and I'll add a few more. Okay, and again, silvers and nitrates randomly strewn around. And now what happens? And again, the key thing from what we added is the cation, because the cation can react with the chemicals here. And the problem we have now is that if silver hits chloride, silver chloride is insoluble, so that'll start to form a precipitate. But silver and carbonate also form a precipitate, so you'll start making this precipitate. And what happens is you'll get these two precipitates kind of mixed together. Each of these forms little tiny individual crystals, but you know when you look at a precipitate, you can't see the individual particles. It just looks opaque because they're so tiny. And so all of those, I don't have enough silvers here, but if I had more silvers, it would fall into one giant pile at the bottom where the carbonates and chlorides are still all mixed together. And you wouldn't be able to separate these tiny precipitate particles. So that one's not going to work because silver precipitates with both chloride and carbonate. So let's get rid of our silver nitrate. And let's see one more thing that we might try to separate the carbonates and the chlorides. So now I'm going to try potassium nitrate. Right, so there's 1 formula unit, and I'll add some other formula units in, just kind of randomly around. Okay, and now what happens? So we're interested in the potassium again, because potassium could interact with chloride, but if you look at your solubility rules, that's soluble, so they'll hang together and then they'll get bounced apart and nothing will happen. Potassium can also try to react with carbonate, but that's also soluble. Okay, so again, they'll hang around but then bounce off. And what you'll see is you're not going to get any precipitate. Okay, all of these ions are soluble with each other, and in this case, you really have no reaction. Okay, so even though we added some additional ions, the chlorides and carbonates are still floating around because we can't make any precipitates. So you've seen one example that works, which was the barium ions that only make the carbonate precipitate. You saw silver not work because it precipitates with both the chloride and the carbonate. And you saw potassium not work because it doesn't precipitate with either. So that's your summary. The key is to check your solubility rules chart and find an oppositely charged ion that makes one precipitate, but not with the other ion you're trying to separate. That's it. This is going to be assessed sort of with question number 4 on the solubility rules worksheet, and that assignment will be coming out.